We're now looking at the first two energy systems. They're considered anaerobic because they don't make use of oxygen. They can't make use of oxygen to break down the fuels. Really just pulling apart the characteristics of the two anaerobic systems, the ATP-CP and anaerobic glycolysis, and just looking at all their characteristics, their contributions to various exercises at various intensities. The key question here is, how do we restore ATP for movement without the use of oxygen? Now, importantly, we're thinking of events here that are probably less than 60 seconds or 75 seconds all up. That doesn't mean that we're not breathing for that whole time. Even in a shot put or a high jump or something that's over in a few seconds, we're breathing. We just can't use that oxygen to break down the fuels for the anaerobic energy systems. That's not how they work.
Now it's time to turn to the two fastest energy systems. They are the anaerobic energy systems, as they work without oxygen, meaning they don't use oxygen to break down any of the stored chemical fuels to help restore ATP. Yes, we breathe while we work anaerobically, but we don't make use of that oxygen to metabolize stored fuels. It's important that you put a lot of time into the tables that are in this PowerPoint and make them your own, and we'll certainly be unpacking all the headings, or if you like, the characteristics or criteria of the energy systems to make sure you can distinguish between peak power, rate, yield, byproducts, etc.
To remind you that the key to energy systems, and feel free to use that abbreviation in your notes, but don't do that in a SAC task or an exam, please. It's not a recognised scientific abbreviation. ATP is, CHO is, CP is, but ES is not. All three energy systems, and we're only looking at the two anaerobic ones now, provide energy to restore ATP. They provide energy to reattach an inorganic phosphate onto ADP and thus replenish ATP. They don't give us energy for movement. Only ATP does that. So the ATP-CP system would be used preferentially or dominantly in any maximum power, strength, speed event up to 10 seconds. So anything shorter than that, if I said get out of your seat and try and touch the roof, the ATP-CP system would be dominant. The way it works like this. Manufactured in our body is creatine phosphate or phosphocreatine. When it splits, the byproducts are creatine and inorganic phosphate. In the process, energy is released from that splitting of CP to provide energy to reattach an inorganic phosphate to ADP. It may well be that the inorganic phosphate that comes from creatine phosphate is pushed back onto ADP as part of the process of CP splitting. In my opinion, a slightly more difficult or complex depiction of that same process is from this textbook. You can draw it however you like, but essentially CP splits. The energy released from the splitting of CP provides energy to reattach any inorganic phosphate onto ADP, thus reforming ATP. You need to play with this table. I know that those of you that did Unit 1, 2 would have a lot of this down. Possibly some new things here are this idea of peak power, which, if you like, is the top rate, the top turnover rate for replenishing ATP within that energy system. So while it might be dominant up to 10 seconds, that's the final range. It could be dominant much earlier and then finish. The top turnover rate for restoring ATP would be within 2 to 4 seconds. In terms of the byproducts and the best recovery, we'll talk more about those when we look at the fatigue and recovery section of the area of study, but just ask questions for things rather than writing them down. Leave gaps in your table if you don't know what you're writing down. Just to help with one of the more common misunderstandings, the CP system, or the ATP-CP system, is the only system that produces inorganic phosphate as a byproduct, and is the only system that may well give its inorganic phosphate to the ADP to restore ATP. Okay? Anaerobic glycolysis and the aerobic energy system, neither of them produce inorganic phosphate. When they break down in the body, they provide energy to reattach an inorganic phosphate from wherever there is one to ADP to reform ATP. Anaerobic glycolysis is the second of the anaerobic pathways, and make sure you use the terminology correctly and read questions carefully. Anaerobic, again, highlighted in blue to signify not using oxygen. It would be dominant, all things being equal, for very high intensity events up to a maximum of 75 seconds. playing with the words we've got, anaerobic's been done for you a number of times, but without oxygen. Glycolysis, if we split it into its two component parts, glyco refers to glycogen and glucose, and lysis refers to breaking down. So it does work obviously with ATP CP system and the aerobic energy system. No one system will ever be exclusively working at any one time. There's always a combination, and it's certainly supported by aerobic events the longer the duration of that anaerobic event. Now, while I like to read things and understand stuff, I realise this is probably not the best way into understanding the chemical breakdown, but if you like reading and make more sense of that than visually interpreting, go for it. I'm going to talk through this when I look at the diagrams over the next slide or two. Try and get your head around some of the language here as you go, but essentially that just in words explains the chemical pathway for anaerobic glycolysis. And in visual format, the same process looks like this. Glycogen, which is the concentrated form of carbohydrate in the body, the chemical form, splits to glucose. When glucose splits, that provides energy to reattach 2 to 3 inorganic phosphate to restore 2 to 3 ATP from ADP. That then does its thing and gives us energy for movement when that splits and that keeps turning over. The byproducts of the anaerobic glycolysis system are pyruvic acid. Now, we don't use oxygen to break that down in the anaerobic glycolysis system, but if in the aerobic system we have oxygen to break that down, something else happens. So without oxygen, which is anaerobic means, pyruvic acid converts to lactic acid, which splits into lactate and hydrogen ions. Now, in terms of glycogen stores, we talk about that because glycogen powers the anaerobic glycolysis system, but also aerobic glycolysis, which is part of the aerobic energy system. So various sources give us various time frames, but up to around 90 minutes is where the average person would have adequate glycogen stores. That can be changed through training, through diet, through carbohydrate loading, those kinds of things. Certainly for an elite Hawaiian Ironman person who's working for 8 hours, they would still have carbohydrates contributing. So there is a great variety, but if you had to pick an average time point, I'd say 90 minutes to 2 hours would be the average glycogen stores of a person. Now, not to get too biology on you, but the anaerobic processes occur in a different spot to the aerobic processes. So the aerobic processes, which we'll talk about next week and which we may have introduced last year, occur in the mitochondria, which is a different part of the muscle fibre. Outside of the mitochondria, in the cytoplasm, is where we get the anaerobic systems doing their thing. So there's a physical movement of fuels and oxygen for various energy systems. Long story short, aerobic energy system makes use of the mitochondria. That's not where the anaerobic systems break down their fuels. For you to draw on for anaerobic glycolysis here, deliberately put in amber, I believe, to say it's the middle of the three energy systems, if you like. If our ATP CP system is super fast, it's probably put green for that. But you can play with colour as much as you like, or keep everything black and white, up to you. Important that you get those terms on the left-hand side down pat. So the rate and intensity, peak power, etc. And ask questions where things are not clear. You will see a range from the various textbooks and internet sites. There is a range for most of these things. As long as you're within a range, you will be right. At the back end of energy systems, we look briefly at fatigue and recovery. And it's just important, I suppose, at this point to realise that in terms of what causes fatigue with this particular system, it's the rapid accumulation of hydrogen ions. So lactic acid used to be what we talk about. It's more precise at the moment to talk about the hydrogen ions. Lactate's actually okay. A large portion of lactate is going to be broken down by the aerobic energy system. So it's going to move from the cytoplasm into the mitochondria, where with oxygen, the aerobic energy system can break it down and give us heaps more ATP. So that's good. Thing is, it's associated with high levels of hydrogen ions, which slow down the muscle's ability to contract.